let us continue our discussion with the what are the rules to decide the plug setting of overcurrent relay, that is phase relay and ground relays. So, the fourth rule, that is the plug setting of ground relays are always lower than the phase relays. This is due to the fact that the magnitude of the earth fault current, that is always lower than the magnitude of current when phase fault occurs. This is basically due to the involvement of the fault resistance in the earth circuit that involves the arc resistance. So, if I consider just the fault value here, fault current, then we have a phase to phase fault and we have a phase to ground fault. So, whenever phase to phase fault occurs, the between two conductors, when this conductor touches, phase to phase fault occurs. So, between these two there is only a arc known as power arc. So, when power arc is there, the value of arc resistance you can obtain with the equation, it is an empirical formula 76 V square by SSC, where V is the system voltage in kV and SSC, that is the short circuit fault MVA at the location of fault. So, using that you can decide the arc resistance, and usually it comes out to be 0.5 to 1 ohm. So, this is fixed, but when you have a phase to ground fault, then the involvement of this phase to ground fault, that involves the fault resistance RF. So, that contains the tower resistance. So, tower resistance, that is usually varies from 5 ohm to 50 ohm. So, that is also there, and if I consider further the other involvement of resistance, then that also contains zero sequence impedance of the system if fault involves the fault is in asymmetrical in nature. So, that is why the magnitude of fault earth fault current, that is always lower than the magnitude of fault current in case of phase to phase fault. The other reason is that ground relays are always connected in the residual circuit of 3 line CTs. So, when we decide the plug setting of ground relays, we need to consider the excitation current of the CT, whereas when we decide the plug setting of the phase relays, then there is no need to consider the excitation current of the line CTs. So, this is very important rule as far as the plug setting is concerned. So, similarly, let us discuss what are the rules to decide the time dial setting of the phase and ground relays. So, time dial setting of phase and ground relay, that is selected such that whenever any relay which is located near the load, that achieves the lowest possible time, and as we move further from downstream relay to the upstream relay, the time dial setting or its value increases. So, time dial setting is chosen such that it gives the desired selective time interval between the downstream relay for maximum fault conditions. For phase relays it is triple line fault, and for ground relay it is line to ground fault. So, what is the meaning of this? The meaning is that, let us say we have a multi section radial feeder network. So, this is section 1, section 2 and section 3. And let us consider we have the relay R1, R2 and R3 connected in section 1, 2 and 3 respectively. Now, when we decide the time dial setting of relay R3, then we have to consider some fault condition, and usually fault condition we consider, that is the fault immediately after the relaying point. Now, if I consider this fault, the fault MVA is not available for this case. So, what we do? We consider normally the fault MVA at this bus. So, for this bus we calculate the time of operation of relay R3, right, for maximum fault current conditions, and then based on this we decide or we calculate the time of operation of relay R2. So, this is the meaning of that thing. So, when we decide the time dial setting of one relay with reference to other relay, we have to consider some margin, that margin is known as minimum coordination margin MCT, or sometimes it is also known as CTI, coordination time interval. So, same example if I consider, when we consider the coordination of relay R2 and R3, we have to calculate time of operation of relay R3, then the time of operation or required time of operation of relay R2, that has to be equal to time of operation of relay R3 plus some minimum coordination time interval or coordination time interval CTI. Now, this MCT, that depends on many parameters. It depends on the for example, what are the errors in the CT, what are the errors in the relay, plus some safety margin. So, based on that, if we consider all these things, then the minimum coordination time interval, that can be considered in the range of 0.2 to 0.3 second. So, here in this case we need to add either 0.2 second or 0.3 second, or in between any value in between these two, and then we have to decide the time of operation of relay R2, and similarly further we need to decide the time of operation of relay R1. So, this is very important point as far as the time dial setting is concerned. The next rule is, while deciding the time dial setting of ground relay, we need to consider the excitation current of CT, as I told you earlier. However, when we consider the two successive ground relay, and if there is a star delta transformer involved between these two successive ground relay, then there is no need to consider anything, no rule is required. You can set both the relay independently, even you can set instantaneous operation also for both the relays. This we will discuss later on, that why there is no need for any such rule when star delta transformer is involved. So, with this background, let us consider the 3 overcurrent and 1 earth fault scheme used for the feeders. Now, what is the meaning of this? So, if I consider relay R1 here, then this R1 is nothing but the group of relays. So, this R1 means group of relay, means we have a phase overcurrent relay and it also have a ground overcurrent relay. So, we have normally 3 units of phase relays and we have 1 unit of ground relays. So, when you have 3 units of phase relay and 1 unit of ground relay, then it is known as 3 overcurrent 1 earth fault scheme. So, 3 overcurrent means 3 units of phase relays and earth fault means 1 unit of ground relay. Similarly, when you consider R2, R2 means also group of relays. So, it has 3 phase relays and 1 ground relays. Similarly, R3 also group of relays, 3 overcurrent 1 ground relay. So, if I consider the network for this, then we have, let us say the 3 conductors are there, RYB or ABC, and we have a free relay connected in each phase. So, in R phase we have a 51A connected, in Y phase we have a 51B connected, and in B phase we have a 51C connected. So, 3 phase relays are connected in each phase, and in the residual circuit we have a 1 ground relay unit, its number is given by 64. So, 64 is the number given for earth fault relay, earth fault overcurrent relay. So, here we have a power circuit and we do have a control circuit like this. So, 51A unit has its contact 51A1, 51B unit has its contact, that is 51B1, and similarly 51C unit has its contact, that is 51C1. So, same way we have a 64 relay. So, 64 relay has its contact, that is 64-1, and we have a 86, that is the auxiliary relay coil and its contact is 86-1, and then we have a 52 TC, that is the trip coil of circuit breaker. So, now let us see how the 3 overcurrent 1 earth fault scheme works. Let us say normal condition, or when there is a double line fault or triple line fault, then how and what the relay works. So, when we consider such type of fault, let us say the phase fault, then in case of phase fault, say in this circuit, let us consider the RY fault occurs. So, in RY fault is a line to line fault. So, obviously phase relay has to operate, it has to detect it, ground relay should not operate. So, whenever in R phase and B phase the current accordingly increases in primary, same way in secondary also it is reflected. So, 2 units are connected, 51A and 51B, these two are energized and it gives signal to its contact 51A1 and 51B1. So, both A1 and B1 will close it, which energizes the coil of auxiliary relay 86, and further its contact 86 trips, and which is going to energize the trip coil of circuit breaker, that is 52 TC. So, this is how the 3 overcurrent 1 earth fault scheme works. If suppose RYB fault occurs, which is a again triple line fault, then the 3 units 51A, 51B, 51C all are energized and their contact 51A1, B1, C1 all are closes and further tripping that is initiated. Now, in case of LL fault or in case of triple L fault, no current that flows through the ground unit, that is 64, because it is a balanced condition. In case of involvement of fault in ground, let us say the R2 ground fault occurs, then what happens, the unit that is 64, the current in the residual circuit increases and its contact, that is 64 trips, and which is going to energize the 86 and further the tripping is initiated. So, in each case, each relay that operates for or that is responsible for the operation of one particular or different types of fault. Now, sometimes it may possible that suppose in this circuit, let us say I have removed the 1 unit, then this scheme that becomes the 2 overcurrent and 1 earth fault scheme. So, let us say there is no relay available in the 51 Y phase, that is 51B I have removed compared to the previous 3 overcurrent 1 earth fault scheme. So, now you can see that if any fault occurs, let us say if RY fault occurs, though there is no unit in Y phase, but in R phase we have a unit 51A. So, 51A operates and the further tripping is given. If RYB fault occurs, then also if there is no unit in Y phase, but we have a unit in R and B phase. So, the R51A and 51C operate and further tripping is initiated. Same way you can consider for the faults involving ground, that is line to ground, double line to ground and triple line to ground. If I remove any one unit out of 3 phase unit, then the same scheme works perfectly well. The only thing happens, only one disadvantage of this scheme is that whenever we have a star delta transformer involved, means any distribution feeder is feeding to the transformer, then there can be a possibility of delayed time of operation. Well, let us consider this with an example. So, again you consider that in Y phase there is no unit, we have removed the 51B from the Y phase. Now, let us consider one star delta transformer and let us assume that we use 2 overcurrent 1 earth fault scheme. So, there is no unit in Y phase. Let us say the YB fault occurs in this case on the secondary side of the transformer. So, on star side, say YB fault occurs here. So, in case of YB fault, the current IY, that is equal to minus IB, and there is no current, ideally very small current in the R phase. So, IR that is equal to 0 and IY that is equal to minus IB. If this is the case, then the current on the other side, delta side, the IR, capital IR is 0, the capital YI that flows here and capital IB that flows, that is exactly opposite of IY. So, if I again calculate IRY, which is a difference of IR minus IY. So, as IR is 0, so we have magnitude wise only IY. If I consider IYB, which is a difference of IY minus IB, so we have a IY and IB both are in opposition. So, the current is 2 IY, and similarly if I consider IBR, which is a difference of IB minus IR, then again IR is 0. So, we have only IY. So, you can see that fault occurs, YB fault occurs, we have removed the unit, phase unit from Y phase, and in Y phase we have a magnitude of current that is 2 times the normal current, right. So, 2 times magnitude of IY current, that current flows are available in Y phase, in which we have removed the unit. So, there are chances of delayed operation in this case, and our objective is to achieve the instantaneous operation as soon as fault or any short circuit occurs. So, this is not possible if I consider the 2 over current and 1 earth fault scheme of instead of 3 over current and 1 earth fault scheme for the protection of the radial network. So, this is very important difference between the 3 over current and 1 earth fault scheme and 2 over current and 1 earth fault scheme. So, with this background we have discussed the plug rules for deciding the plug setting and the ground setting of the phase and ground relays. We have also discussed the 3 over current 1 earth fault scheme and 2 over current and 1 earth fault scheme. So, now let us solve one example. This example is basically for deciding the setting of different relays. So, how we coordinate the phase relays, phase over current relay, that is that can be decided. So, in this example the single line diagram of the network is given, that is shown here. You can see that there are 4 relays connected, R1, R2, R3, R4, and all this R1 to R4 all relays are IDMT overcurrent relays having normal inverse characteristic. Further, at each bus, bus A, bus B and bus C, the fault level in MVA that is mentioned. So, you can calculate the magnitude of fault current at each bus utilizing this, because the voltage level is also given. The rated current of all these relays are 1 ampere. So, this relay rated current is same as CT secondary current, as I told you. So, relay rated current of all relays R1 to R4 are 1 ampere, and its plug setting range is from 50 to 200% of rated current in steps of 25%, whereas the time dial setting range is 0 to 1 second in steps of 0.05 second. And the plug setting and time dial setting of relay R4 is given. So, we can say that the plug setting of relay R4, that is 100%. So, plug setting of relay R4 is 100% of 1 ampere, that is relay rated current, and its TDS value that is also given, that is 0.1. So, plug setting and time dial setting of relay R4 is given, and you need to calculate the plug setting and time dial setting of all other 3 relays, that is R3, R2 and R1. So, let us solve this example considering that the R1, R2, R3, R4 are phase relays, and let us solve this example. So, to solve this, let us consider the same figure. So, we have a generator connected with generator transformer, and then we have a bus, that is bus A, and then we have a relay connected somewhere here. So, that relay is R1, right, and the magnitude of fault level at bus A is 2500 MVA. Then we have another feeder connected here with bus B. The relay connected here, that is say R2, the fault MVA level at this bus, that is 2000 MVA. And then we have the another feeder connected here, that is the connected to the transformer here, and then we have another bus. So, one relay is connected here, that is let us say the R3, and its CT ratio is 400 by 1. The CT ratio of R2 is also 400/1 ampere, and the CT ratio of R1, that is also 1000 by 1 ampere. With this background, again at this bus, this is a 132 kV bus, and the fault level that is given is 1000 MVA here, and we have a different feeder from this bus. So, the different feeders are available, and let us assume that on one feeder we have a relay R4 whose plug setting is 100% and TDS that is given as 0.1. The CT ratio of R4 that is given as 200 by 1 ampere, and the rating of this transformer that is given as 220 kV by this bus is 132. So, it is 132 kV, and the MVA rating is 100 MVA, and it winding connection is dy11. Same way we have the transformer here other on the left hand side of relay R1 and its value is 13.2 kV by obviously the line is 220 kV, this line is 220 kV line. So, the transformer ratio is 220 kV and its MVA rating is 250 MVA with the connection dy11, and this transformer is known as it is connected to generator, it is known as generator transformer. The generator rating is also given, that is 13.2 kV, its MVA is megawatt value is 210 megawatt at 0.85 power factor. So, with this background let us solve the example. We need to find out the plug setting and time dial setting of R1, R2, R3 relays. So, let us start the solution with plug setting. So, let us decide the plug setting of relay R3. So, as I told you, the relay R3 plug setting is decided based on the plug setting of relay R4. So, as I told you earlier, plug setting of relay R3, that is greater than 1.3 divided by 1.05 into plug setting of relay R4. So, if I consider this, then the plug greater than 1.3 1.05 into plug setting of relay R4. So, plug setting of relay R4, that is given as 100% of 1 ampere, that is the relay rated current. If I consider it based on the primary value, then it is 100% of 200 ampere. So, it is 200 ampere. So, that comes 200 here, and you can also visualize that there is a transformer between relay R3 and R4. So, we need to multiply the ratio also from 132 kV to the 220 kV. So, that also comes here. So, if you solve this, then that comes out to be roughly around 148.57. This is on primary side of relay R3. If I convert it on secondary side, so I have to divide it by its city ratio, that is 400 ampere. So, the value available, that comes out to be 30.3714. So, if I write in percentage, 37.14 percentage. So, obviously based on this we can decide the setting, that is 50%, because the setting range of all the 4 relays, that is from 50% to 200% of 1 ampere in steps of 25%. So, higher value beyond 37.14%, that is the available, that is 50%. So, we can decide the setting of relay R3, that is 50%. So, if I decide plug setting of R3, that is 50% by this rule, then we have to also cross check that the relay R3 should not operate in case of when the transformer draws a full load current on 220 kV side. So, if I just find out the rated current of the transformer on 220 kV side, then that is given by 100 MVA divided by root 3 into 220 kV. So, if you solve this, then that comes out to be the value, that is roughly around the 262 ampere. So, 262.43 ampere, that is the current. If I convert this on secondary side of relay R3, then I have to divide this 262.43 by city ratio of R3, that is 400. So, this comes out to be roughly around the value, that is 65.61 percentage. So, the setting of relay, plug setting of relay R3 should be greater than this. So, next range available greater than this, that is 75%. See, in earlier case if I utilize this rule, the setting comes out to be 50%, but when I check the rated current of the transformer, then the setting comes out to be 75%. So, I have to select higher value, that is 75%. So, plug setting of relay R3, that is 75% of its rated current 1 ampere or 75% of primary, that is 400 ampere. So, now let us decide the plug setting of relay R2, because next relay towards the source from relay R3, that is the relay R2. If I want to decide the plug setting of relay R3, then you have to, what you have to do is, let us write down the plug setting of relay R2, that is greater than 1.3 1.05 into plug setting of relay R3. So, that is 1.3 1.05 into plug setting of relay R3. So, plug setting of relay R3 we have selected as 75% of 1 ampere or 75% of 400 ampere. So, here that is the 75% of 400 ampere. So, if I just solve this, then the value available, that is greater than, if I just solve this value, then the value comes out to be roughly around, the value is say 371.42 ampere. So, 371.42 ampere. So, if I again reproduce it on secondary side of R2, then you can see that the CT ratio of R2 is 400 by 1. So, if I convert this value 371.42 divided by 400, then the value available on secondary side in percentage, that is 92.85%, right. So, obviously we can select the next setting range available higher than this, that is 100%. So, plug setting of R2, that can be selected as the 100%. So, now let us decide the plug setting of R1. So, plug setting of R1, that can be decided based on again two rules. You coordinate relay R1 with relay R2. So, if I just do it the coordination, then plug setting of R1, that is greater than 1.3 upon 1.05 into plug setting of relay R2. So, that should be greater than 1.3 1.05 into plug setting of relay R2. So, plug setting of relay R2 is 100% of 400 ampere. So, that is 400. So, if I solve this, then the value comes out to be 495.238 ampere. If I convert it on the secondary side of relay R1, then you can see the CT ratio of R1, that is 1000 by 1. So, if I divide it, the value comes out to be 49.52 percentage. So, we can say that we can select next higher range, that is 50%. But at the same time, we need to also look at the relay R1 is connected on 220 kV side of this generator transformer. So, let us see even what is the full load current of the generator transformer. So, if I just calculate the full load current of transformer, that is GT, then the rated current of the transformer on 220 kV side, that is given by, the rating is 250 MVA. So, we can say that it is 250 into 10 raised to 3 divided by root 3 into 220 kV. So, the value comes out to be 656.08 ampere. If I convert on secondary side, I have to divide it by 1000 because that is the CT ratio of R1. So, 656.08 divided by 1000. So, the value comes out to be in percentage, that is 65.608 percentage. So, whatever setting we select, the next available setting range, that is the 75%. So, in earlier case we obtained 50%, in this case we obtained 75%. So, we will consider the setting of plug setting of relay, that is higher value, that is 75%. So, plug setting of relay, we have R1 we have decided, that is the 75%. So, we have now decided the plug setting of R1, we have calculated the plug setting of the R3, we have also calculated the plug setting of R2. So, first task we have completed. Now, in the next class we will decide or how to determine the time dial setting of relay R3, then R2 and then R1. So, in this class we started our discussion with what are the different rules to decide the plug setting and time dial setting of phase relays and ground relays, and then we started one example, that how the coordination of phase over current relays, that is to be carried out. So, coordination means we need to decide the plug setting and time dial setting of relays. So, we have considered one example and we have determined the plug setting of 3 relays R1, R2, R3. In the next class we will decide the time dial setting of 3 relays, that is R3, R2 and R1. Thank you.